Hi, thank you for tuning into this episode of Diapharma's The Science Behind. I am Matt Sobo, a scientific product manager at Diapharma. Today, we will discuss the science behind the Thrombodynamics system manufactured by Hemacore. Please visit our website at www.diapharma.com or send us an email at info@diapharma.com. As a brief reminder, the coagulation system is a process used to plug damaged vasculature with a fibrin plug. Disruption of the endothelial surface exposes tissue factor to the blood. This sets a cascade of reactions, known as the coagulation cascade, that penetrates into the blood that leads to the formation of fibrin, as well as sowing the seeds of its own dissolution. You can learn more about the coagulation cascade in another video on our website. In the context of bleeding and clotting, these processes must be able to be observed, monitored, and tested for a variety of reasons, including identifying defects that could lead to blood loss or learning about the efficacy of a pharmacologic inhibitor of a member or multiple members of the cascade. The problem stems from the fact that coagulation in vivo is not the same as in vitro. In the body, the clot will form locally, triggered by local signals at the site of injury. Clot propagation occurs in space and time and remains local. The various coagulation tests employed, for example, the prothrombin time, the active partial thromboplastin time, the thrombin time, the class fibrinogen, as well as many others. All of the reagents and enzymes are put into a single tube and mixed up really well. The time to the formation of a clot is then measured, either mechanically or photometrically. The clot forms everywhere all at once and is incapable of shedding light on the dynamic nature of the coagulation cascade or clot formation. Thrombodynamics seeks to reconstruct physiologic conditions that allow for understanding of that dynamic nature of clot growth in time and space. Plasma sample is added to a cuvette and an activating insert is lowered into the plasma. This activating insert is coated with a lipidated tissue factor at concentrations that mimic the endothelial lining of the damaged vasculature. By means of light scattering registration, one can see how the fibrin clot propagates in space from the activator. For this slide, a PT test was performed in the Thrombodynamics cuvette without addition of the insert and compared to the Thrombodynamics test with the insert. At activation, there is very little difference between the two. By 5 minutes, significant general clotting can be seen in the test above, while the Thrombodynamics test below shows a clear clot front that has progressed a short distance from the activator. By 10 minutes, the routine test is a wash and clot signal, while the front line of the Thrombodynamics test has progressed further into the plasma. At 30 minutes, the routine test looks the same as it did at 10 minutes, while the Thrombodynamics continues to penetrate deeper into the blood. As mentioned earlier, the time to initial clot formation is all that is measured by the routine test and would have completed even before the 5-minute image here. However, the moving front and intensity of the clot signal allows for easy visualization and dynamic data reduction and quantification for plasma that is hypercoagulable or hypocoagulable. It is even able to detect clots that are not being driven by endothelial tissue factor, severe hypercoagulation, as spontaneous clots. The parameters derived by Thrombodynamics include the lag time, which is the time between the start of the test and when the fibrin clot can first be detected above background. The initial rate of clot growth, which is measuring the early drivers of clot formation and tissue factor. The stationary rate of clot growth measures the drivers of coagulation as the clot moves away from the activating tissue factor. The size of the clot 30 minutes after the assay starts, and the density of the clot, which is primarily measuring fibrinogen and is visualized by how bright and intense the clot front is. As I mentioned earlier, spontaneous clots are fibrin deposition that are not connected to the front line and caused by something other than tissue factor. Simple addition of a fibrinolytic agent or inducer, such as TPA, allows Thrombodynamics to measure fibrinolysis as well. Automatically derived parameters include the lysis onset time and the lysis progression, measuring how quickly the clot is being broken down. Also, with minor modifications, clot contraction, the last phase of clot maturation linked to platelets pulling on fibrin strands and reshaping of the blood cells to remodel the clot, can also be studied. As an option, a fluorescent module is available, which allows for the additional measurement of thrombin generation spatiotemporal dynamics. Here we visualize the thrombin generation potential near the activating surface and 1 millimeter away from the surface. The time delay to start of thrombin generation and differences in peak thrombin generated at these locations are clear. In addition to the parameters derived in the standard Thrombodynamics method, Thrombodynamics 4D derives the lag time to thrombin generation initiation, the peak thrombin generated at the activator's surface, and the peak time to reach said peak in thrombin generation. Total thrombin potential at the activator's surface is also measurable. Also, the moving peak thrombin generated measured as the stationary amplitude. The rate of thrombin peak progression measuring how quickly into the blood thrombin generating reactions are progressing. Thank you for watching this episode of The Science Behind, where we discussed Thrombodynamics and Thrombodynamics 4D. You can find additional informational and educational videos on our website, www.diapharma.com/videos. If you have any questions, please reach out to us at info@diapharma.com or visit our website, www.diapharma.com. We'll see you next time.